All right, let's jump right in. If you're gearing up for the AP Computer Science A exam, this is something you absolutely got to nail down: how Java handles different kinds of data. I know it sounds kind of small, but trust me, getting this right is the secret to dodging some of the most common and most frustrating bugs in all of programming. To really get a handle on this, I want you to forget about the code for just a second. Picture this. Every single variable you create in Java is just a container. And the data you put inside, that's the liquid. The whole secret to understanding this stuff is just knowing the size of your container and what happens when you pour from one to another. Right, so just like in real life, you wouldn't use a tiny shot glass to hold a whole gallon of water. Java's no different. It has all these different data types, and they're all built to hold different amounts of information. Let's size them up.
Okay, check this out. This table really makes that whole container idea click. A byte, think of it as a little shot glass. It can only hold a number between -128 and +127. An int, which is probably the one you use the most, that's like a solid picture. It can hold values all the way up to about 2.1 billion. And then you've got the double. That's our industrial-sized bucket made from massive numbers, and this is key for decimals. Okay, so we've got our containers. Now for the fun part: actually moving the data between them. In Java, the official term is casting, but honestly, just think of it as pouring. And it turns out there are two very different ways you can pour. So on one hand, you have the easy pour. Programmers call it implicit casting. This is when you pour from a small container, like a pitcher, into a big one, like a bucket. It's totally safe, right? Nothing's going to spill. So Java's cool with it. It just does it for you automatically. But going the other way, from that big bucket into a small pitcher, that's what we call the forceful pour. And that's risky. You could lose some data. So Java basically puts its foot down and says, nope, not unless you give me explicit permission. Let's see what this easy pour actually looks like in the code. We've got an integer, 100, and we're putting it into a double variable. Because we're going from a smaller container, the int, to a much larger one, the double, Java just handles it. No special commands, no fuss. The integer 100 smoothly becomes the decimal value 100.0. Easy as that. But what about this situation? We've got a double, 99.7, and we're trying to shove it into a smaller int container. Now Java's going to throw up a red flag unless you use this very specific command, int. You can think of this as your special funnel. It's you telling the computer, yep, I know this is risky, I know some data might get chopped off, and I'm okay with that. And look what happens. The decimal part, that 0.7, poof, it's gone. The integer myInt is now just 99. All right, so this whole idea of losing data, it leads us to one of the wildest, most surprising things in programming. What actually happens when you try to put way too much into one of these containers? I mean, think about it. What does happen when you try to pour a gallon of water into a tiny cup? In the real world, you just get a huge mess. But in the digital world, well, something even stranger happens. So let's do an experiment. We're going to take our int container, that pitcher, and fill it all the way up to the absolute brim. The maximum value an integer can possibly hold is this crazy huge number, 2,147,483,647. It is completely, totally full. And now, we're going to do something that seems totally innocent. We're just going to add 1. That's it. Logically, you'd think maybe you'd get an error, right? Or maybe the whole program would just crash. Well, that is not what happens. Not even close. Boom. Just look at that. The number doesn't just get a little bigger, it completely flips. It wraps around all the way to the most negative number an integer can possibly be. It's like the container didn't just spill, it teleported its contents to the complete opposite end of the universe. So this crazy thing actually has a name. It's called overflow. And when it happens on the other end, when you go below the minimum value, that's called underflow. This is a fundamental rule of how computers work with numbers. When you run out of room, the numbers just wrap around. This is a huge deal for the AP exam. And trust me, it's the source of some of the sneakiest bugs you'll ever find. Okay, so now that we know the dangers, let's flip this around. How can we actually use casting as a tool? It turns out that a very precise, controlled pour can be the exact thing you need to fix a really common bug. You've probably run into this one. It's a classic problem that drives so many people crazy when they're starting out. You ask the computer to divide 5 by 2. You know in your head the answer is 2.5,
But look what Java gives you back, 2.0. So what's going on? It's because when you ask Java to divide an integer by an integer, it feels obligated to give you an integer back, so it just chops off the decimal completely. Let's see how we can fix this. So how do we fix it and get the right answer? The solution is surprisingly simple, and it all comes back to that controlled, forceful pour. Look at the fix step here. By putting double right in front of the sum variable, we are temporarily promoting it. You're basically telling Java, hey, hold on, before you do this division, I want you to treat this sum variable as if it's a big bucket, a double. And that one tiny change forces the entire calculation to be done using decimal math, which finally gives us the correct answer we were looking for, 2.5. It's a tiny piece of code, but it has a huge impact.
Okay, let's wrap this all up. If you're studying for the AP exam, you can just think of everything we just talked about as a simple set of rules for safe pouring.
So here's what you got to remember. Pouring from small containers to big ones, that's widening. It's automatic and totally safe. Pouring from big containers to small ones, that's narrowing. You have to give permission with an explicit cast, and you always risk losing data. Next, every single container has a limit, a max and a min. If you go past it, you get an overflow or underflow, and the value wraps around. And finally, you can use a controlled, explicit cast as a tool to fix annoying bugs like integer division. And I really want this to sink in. I know it seems like we're just talking about losing a decimal point here and there, but in the world of computers, there is no such thing as close enough. A number that's off by 0.0001 isn't almost right. It's a completely different number, and the computer will follow the logic of that wrong number to whatever conclusion it leads to, no matter how catastrophic. So next time you're coding, think bigger. This stuff isn't just about passing a test. How could one little, unseen overflow bug affect a financial calculation for a massive bank? What could a single misplaced cast do to the trajectory calculations for a multi-billion-dollar spaceship? Understanding these fundamentals, this is the first step to writing code that doesn't just work, but code that's safe and reliable.